So let's start discussing how do we estimate how many samples we need if we want to compute the probability or the mean of something using Monte Carlo method. So we have already seen in the last lecture that when we use fewer samples, we are going to get more variabilities, which means we cannot trust our result that much. So we'll start by this lecture by analyzing that more mathematically. So how much error does too few samples lead to? We want to not just say qualitatively that using fewer samples leads to wider variations. We actually want to compute quantitatively how much error does too few samples lead to. And what is an extreme of too few samples? Well, we can think of the case, how about if we use just a single sample? It sounds a little bit ridiculous, but it's actually a pretty good place to start. So we'll start by saying, okay, what if one sample is used? Okay, so it's used for what? In the last lecture, we computed the probability that our spacecraft is going to collide with an asteroid. So we were estimating the probability. If a single sample is used, the outcome is either crashed or not crashed, right? So the result is either 0 or 1. So we'll be estimating how much error does that probability of 0 and 1 make. And this analysis is actually more general than that, because remember, the probability is simply the mean of a 0, 1 random variable, right? Now, so essentially, we are trying to estimate the expectation of a random variable, let's say x. We are approximating that by a single sample of that random variable x1, right? So this is a single sample of x. In the last lecture, we have been dealing with a particular case where x is a 0 or 1 random variable. It is equal to 1 with a probability p, and 0 with probability 1 minus p, right? So for this particular case, our expectation is of this x is what? Is the value of the random variable 1 times the probability that it takes 1 plus the value of the probability 0, the value of the variable 0 times its corresponding probability, right? So 1 times p plus 0 times 1 minus p. That's the average value or expectation. So that's the expectation. Of course, that's just equal to p. So essentially, if we want to compute the probability that this random variable is equal to 1, well, we just take its expectation. Okay, and we have been using the formula that we average, right? We average over the n samples. And in this particular case, if we just use a single sample, we'll just be taking the value of the single sample, which is either 0 or 1 in our previous case. If we crash, the value is 1. If we don't crash, if it's 0. It's going to be a terrible estimate of the probability, right? The task we are discussing this page is to figure out exactly how bad it is. Now, how do we quantify how bad it is? A usual measure of quantifying how bad some random estimator is by looking at its what's so-called the standard deviation, right? So standard deviation estimates how variable an estimate is. Okay, so in this case, we have this particular estimate, right? And we want to figure out how much it varies from the true value. Actually, let's discuss not standard deviation, but the standard error first. The standard error is indicating not how variable, but how variable an estimate is from the true value. And in this case, we want to estimate the expectation or the population mean of a random variable. And we estimate it using just the value of a single sample, right? So the standard error, it's supposed to estimate how that single sample is going to deviate from the mean, okay? And so let's basically put down the definition first. So let's say X is an, or let's just change the variable name. Let's say Y is an estimator for a number, right? For a number, for an unknown number, let's say, because otherwise we wouldn't need a probabilistic estimator for that. Y. So in this case, our unknown number is the expectation of X, okay? And we want to estimate it with just a single sample of the random variable itself. So standard error is defined as the square root. So let me write down the square root, right? Something to the half power is the square root of the expectation of big Y minus small y squared. Okay, so what does this mean? It means we have a big Y that's a estimator that behaves probabilistically, right? Remember, in the last lecture, we estimated the probability with a procedure, right? We counted how many of the samples would lead to a crashing with the asteroid. And the fraction of crashes we computed actually depended on exactly what kind of samples I got. If I reperform the samples, if I reperform the sampling with exactly the same procedure, my number is actually going to change a little bit. If I take less samples, my resulting estimate of the probability would vary over a wider interval. That's what we mean by the estimator being probabilistic, right? So that's our big Y. And the small y is the true probability, the probability that we would get if you use infinitely many samples. That's actually a number without variability, but it is an unknown number. So the standard error is a measure of how much the imprecise estimator that varies stochastically differs from the true number that doesn't vary. And because the estimator is probabilistic, we want to measure with an expectation the average variation, right? And the average variation is in the square sense. We are looking at the average, the squared difference between the true value and the estimator, and to take that to the same unit as the estimator, as the true number itself, we take a square root. So that's what we mean by